So in this final electric fields video, we're going to look at what happens with the electric field due to a pear-shaped conductor. And really we're looking at a pear-shaped conductor to look at what happens with the electric field strength near a sharp point. And that is going to flow in really nicely to what happens and how a photocopier and also a laser printer work as well. So, final electric field we want to look at is the electric field due to a charged pear-shaped conductor. So here's my best drawing of a pear-shaped conductor, and I'll demonstrate this one on the Van de Graaff generator in class as well. You can either do it with a pear-shaped conductor or just using a sharp point using like the back of the ball that you use on the Van de Graaff generator, where you will hear that discharge. We'll talk about why that discharge happens in a sec. So firstly, the charge will accumulate, if you like, near the sharp point. So we'll get more charge near the sharp point, and that means that the electric field will be strongest in that region near the sharp point. And then as we move away from that sharp point, we will get the field not as strong, so weaker, and basically in this region we'll get where we've got this sort of constant radius, the field will, how am I going, be relatively uniform. Now this is a positive charged plate, probably should indicate it's even stronger in this field. It is very strong. So there's our fairly crudely drawn electric field diagram around a pear-shaped conductor, showing that basically it is much stronger near the sharp point, therefore the lines are much closer together. And what you will actually see, and you'll hear this when you do this on the Van de Graaff generator, is that the electric field will get so strong in this point here that it will actually ionize the particles in air. So it'll turn the oxygen and the nitrogen atoms into ions. Ions can conduct electricity. So firstly, they get lots of energy put into them, so they basically glow. That's why you get the spark. That spark is a flow of charge that can conduct electricity a lot, like when you get the discharge on the Van de Graaff generator. So due to this sharp field, we can get, that's supposed to represent a spark coming off in that region. So the ionizing of the air, which is basically that spark, or when I know in the class I put the handle of the ball that goes with the Van de Graaff generator, you can hear that constant discharge. If you could do that in the dark, you would actually see that faint blue glow of the air particles in that region due to that constant discharge, due to the field being so strong that it ionizes the air particles. So firstly, I want you, if you haven't already, to make sure you have a look at this video here, The Secret Life of Photocopiers. You can either probably Google that or go to the address here in this link, and that'll take you straight there. Gives a really, really good insight into how a photocopier works. Does come with a warning that it does contain some inappropriate 1950s humour, maybe we might say. But no, it's pretty good. So let's talk about, in terms of electrostatics, how a photocopier works. In essence, within a photocopier or within laser printers, we have this drum in the middle that's spinning. If you've ever pulled a cartridge out of one, you probably would have seen these drums. They're often covered in toner particles, which is basically the ink. So it is a cyclical process, but we'll start up here. The first thing we have is a very tight radius, so a very fine wire. That tight radius creates a really strong electric field, which creates a corona discharge, which basically in this case, is a positively charged corona wire, and that is very close to the drum, and that sprays, if you like, charge, positively charges up the drum. This drum is made of a material that will lose its charge if it's exposed to light. So it's called photoconductive. When it sees light, it conducts the charge away. If there's no light, the charge stays. So the image is exposed onto the drum, so we've got a little face here, and the drum will lose its charge wherever there's light, but wherever the image was and there wasn't any light exposed, those areas will remain charged. The toner particles are then attracted to this positively charged drum. So we basically get an image form on the surface of the drum. At the next phase, we have some paper come in. Now that paper first goes over a negatively charged corona wire to charge up the paper with the opposite charge to the drum. It then runs very close to the drum, and the opposite charge causes the toner particles that are on the drum, so they've spun around to here now, to be transferred onto the paper to start to create that image that we had back up here. Then the final thing is we get left with this charged up bit of paper, and charged paper tends to curl and be very difficult to manage. So that piece of paper then is passed by another positively charged corona wire that basically neutralises the negative charge that the paper had here. And that is, in a very simple sense, how a photocopier and many laser printers work. That's it for the electric fields topic. So in the next topic, we're going to continue with the theme of electric fields, but we're going to look at the motion of charged particles inside electric fields.